Welcome to my presentation entitled Cost-Effective Characterization of the Fatigue Behavior of PBF Metals. My name is Gianni Nicoletto. I'm Professor of Machine Design at the University of Parma, Italy. I begin my presentation with an overview of the problems that are involved when we want to test for fatigue PBF metals. First of all, we do the testing in the framework of process and material qualification. This is a long process because there are a number of variables besides materials and equipment that need to be considered and optimized. The fatigue properties are typically obtained at the end of the optimization process, but they are fundamental if the application is of a structural type. Fatigue testing is typically and frequently performed on standard specimens with machined surfaces, because that's the classical approach for material characterization in mechanical engineering. But if we consider, however, the part design and development phase, the situation is quite more complex. Here we see an example, a part that is clearly of a complex geometry and obtained by topological optimization. We see on the right side the part still on the build plate with supports and the original as printed condition. Of course, to obtain the final version of the part, we need to do some post-processing, but the post-processing is typically limited in terms of the cost because it's very expensive, or even feasibility. You cannot really machine surfaces as complex as those shown here. So in general, if we have to develop a part subjected to fatigue loading conditions, we need to also determine fatigue data that are connected to these specific characteristics of an additive manufactured part. Therefore, there are a number of challenges in fatigue testing. The first challenge is the cost. Material testing in this kind of technology is quite expensive because the metal and the metal powder is very expensive. The systems that are used for producing specimens or parts are very expensive to operate. In addition, as we saw, there are a large number of technological factors that are important and that are optimized to get the best properties. And finally, the fatigue testing typically requires many specimens, even for the generation of a single curve. So in addition to this challenge, there is another one, and it's related to the complexity of the PBF process. We have seen that we have to deal with parts that could have surfaces in the as-built condition. So we need to determine knockdown factors specific in fatigue for determining the lifetime of those objects. We saw geometrical complexities like notches, reentrant corners, which we know are important for the fatigue strength of the part, and so we need to determine also the influence of those features on the fatigue behavior. And finally, there are also still open issues like homogeneity or stability or transferability of the material properties that are thus determined. So there are needs in the additive manufacturing sector that we think can be summarized here. We have to contain fatigue testing costs because we saw that there are a lot of variables involved, and so we would need to do a lot of fatigue tests to qualify materials and processes. In addition, we have to consider specific features of the additive manufactured parts and how those features influence the fatigue behavior. Okay, we answered to those needs with an innovative test method that's shown here, and it's based on the concept of miniaturization. We see in the picture a mini specimen, 22 mm long, compared to the standard push-pull testing specimen. This mini specimen is loaded cyclically in bending according to the scheme shown here. In this way, we can control the crack initiation location and therefore the fatigue behavior as a smooth surface condition. To apply this cyclic bending moment, we developed a testing machine specific for this small specimen, working at 25 Hertz, and it's an electromechanical system that continuously monitors the load during the test and easily can perform, let's say, fatigue test in the long range. We performed the validation of the methodology by comparison, considering data from the literature, as in this case for aluminum silicium 10 magnesium. The reference data was obtained by rotating bending, and combined to the data, the reference data, we have the dark symbols that represents the mini specimen test results, both in the case of as-built surfaces and in the case of machined surfaces. You can see that the correlation among the different sets is quite good. We continue here with a comparison of our miniature specimens results with cyclic tension data, again from the literature. In this case, it's an electron beam produced titanium. And you here again have a good correlation between the miniature specimen data and the standard data. A brief discussion should be now introduced on the role of as-built surfaces in additive manufacturing. We say that post-processing is very costly, so it's important to make the technology competitive, that the surface post-processing is minimized. But since we have this problem, we have also to learn how to deal with rust surfaces, especially when we have to develop a part. Here we see the characteristics of the as-built surfaces. As shown in the picture, we have, for example, hatching configurations, we have contour pattern, and also we can see on the right side how the surface is rough because of partially melted particles attached to the surface. We can also recognize how the orientation of the surface with respect to build directions generate features that are completely different, and therefore we can expect that the fatigue behavior is influenced by it. The method that we propose is not only cheap, but it's also flexible. According to this scheme, we can see that we can test in fatigue different surface orientations. Here we can see the build that has been developed, where you can see a number of Inconel specimens, a large number of Inconel specimens oriented in different directions. And the total of 246 miniature specimens amounted to only 1.5 kilograms of material in the end. So it's really cost effective. The specimens with the different surface orientations have been tested in fatigue, and here in this plot we see the results. we can see that there are differences among the different orientations. Especially there are 3 orientations that lead to similar trends, but there is one specific orientation, the 45 minus orientation, that is characterized by clearly better fatigue response. This diagram, it's part of a larger presentation that we are going to give in a future conference, ICAM 2021, for the interested people. The behavior that we see here in fatigue has been also investigated in terms of the original surface quality. Here on the right side, on the top diagram, we see the different surface roughness parameters measured for the different inclined surfaces. We can see that the roughness changes significantly depending on the orientation as expected. On the bottom, we see also views of the surface morphology as obtained by an optical profilometer. We investigated the role of residual stresses in fatigue. We selected an aluminum alloy that we treated by a direct aging low temperature heat treatment. In this way, we expected to have a material with residual stresses still present in them. We prepared the specimens oriented in the horizontal and in the vertical directions, and we determined by simulation the residual stresses in the specimens. We found that the vertical specimen is characterized by very large tensile residual stresses, while the horizontal specimens have a negligible level of residual stresses. We tested those specimens and we determined the data that are shown in this plot. Again, you can see that the horizontal specimens give a very good fatigue response. Those are the specimens without residual stress in them. On the other hand, the vertical specimens perform very differently and with much lower performance because of the presence of these high tensile residual stresses. We also investigated the notch effect in fatigue. What we did was essentially to apply a bending moment like this, like shown in this scheme. This loading condition generates a stress concentration factor of about 1.6, so we call it a mild effect. And once we have this characterization, we can develop and produce specimens with different orientations of the notches. So we can investigate the directional notch effect in fatigue. And this diagram shows the set of data that were obtained for the 4 directions of the notches. You can recognize that there is a large difference between fatigue data, the best fatigue data and the worst fatigue data. They range from 260 for the best orientation, which is the type B orientation, to 130 for the type A plus orientation, which is the DOWNSKIN orientation of the notch. Graphically, here we can compare UPSKIN and DOWNSKIN notches. We can see on the left side the quality of the surfaces obtained depending on the orientation, and on the right side we have the evidence on the fatigue behavior. We obtain for the UPSKIN the red curve, and we obtain the blue curve for the DOWNSKIN orientation. So DOWNSKIN, as expected, is providing us with a worse response this response is coherent with reference data obtained by UPSKIN with a different specimen geometry, but rather similar KT value. We also investigated notch severity in fatigue. Therefore, we consider the mild notch geometry that we already tested, and we also prepare specimens with a sharp notch in them. The sharp notch achieves a stress concentration factor of about 5, which is significantly larger than the mild notch stress concentration factor of 1.6. We performed testing on those notched specimens and determined the data in this plot. We have the reference data for the smooth configuration, and we achieve for those a fatigue strength of about 300 megapascal at 2 million cycles. When we test the notch specimens, we determine different fatigue strength at 2 million cycles. The difference is quite significant, and it's related, of course, to the level of stress concentration. We go to 210 megapascal for the mild notch effect, and down to the 130 megapascal for the sharp notch specimen configuration. The test methodology that we have been developing is now applied in industry. We have a number of cooperations ongoing. With BMIT, we are investigating the problem of process optimization and fatigue data generation. In addition, we are investigating the possibility of using the miniature specimens as witness specimens, as you see in this picture, where according to this picture, we see the specimens along with the parts, the actual parts, so we can test miniature specimens produced simultaneously with the part that are to be qualified. In addition, we are cooperating with Ferrari, sector is automotive, of course, on the new aluminum alloys and the influence of surface finish on fatigue properties, and the miniature specimen method is used also for part qualification. Finally, we are cooperating with ESA, so space sector, in testing of Inconel 718, the influence of different surface finish techniques, and the correlation of our data with reference standard data. We arrive now at the conclusions. First, the structural design of safety critical parts require representative fatigue data. Specimens with machine surfaces may not provide useful data if the part have to have as-built surfaces for cost reduction. The miniature specimen test method is characterized by remarkable flexibility demonstrated by experiments in this presentation and by results that are coherent with reference data obtained with standard specimens. In addition, the specimen miniaturization approach drastically reduced fatigue testing costs. We apply this method now successfully to a number of materials. We investigated aluminum, Inconel 718, and titanium extensively. The miniature specimen test method is currently used in industry. So if the researcher is interested in the method proposed, I welcome the possibility of providing us with a set of miniature specimens. We will blindly test them, and at the end we can jointly publish the results and the comparisons with maybe standard specimen tests. Thank you for your attention.